everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a very important topic in semiconductors, that is classification of materials. So let us see the brief outline of this module. Initially, we have discussed the free electron theory in three different stages. First, we have seen the classical free electron theory, where the electron is free to move anywhere inside the metal. And then we have seen the quantum free electron theory, where we have considered that the electron is moving in a in a constant potential, and we assumed that the potential is zero. And in order to explain the periodic potential, we have the Bloch theorem, where Bloch introduced the periodicity with the help of a Bloch function uk of x. And then the application of Bloch theorem we have seen in the chronic penny model, where we are discussing about the bands. The bands where the electron can be in the bound state or in a free state. That is what we have discussed in the chronic penny model. But when we have seen the electron theory, we have seen that these theories failed to explain the classification of materials. Classification of materials into conductors, semiconductors and insulators. That was a big failure of the free electron theory. So today we are going to understand the classification of materials by using the band theory. So let us first try to understand the origin of energy bands. So how do these bands originate? That is what we are going to understand first. And then we will see what a valence band is, and then a conduction band. Then we will see the classification based on energy band diagrams. How we are going to classify the materials with the help of these energy band diagrams. Now, if we see, whenever we are talking about atoms, we are saying that in an atom, there are electrons, and these electrons are tightly bound to the nucleus. So we give the representation whenever we have to show a particular atom, there is a nucleus at the center and electrons revolving round the nucleus in fixed orbits. And the energy of these electrons is fixed. That is what we understand. But what is happening here is they exist in discrete sharp energy levels. Discrete here means it is not continuous. So the energy of this level is different from the energy of this level. Means the energy possessed by these electrons is E1. Then the energy possessed by these electrons in the next shell will be E2. So they exist in sharp energy levels which are discrete. And the energy of the electron depends upon the orbit it is revolving in. You can calculate the energy of the electron. We have derived the formula also to calculate the energy. E is equal to n square h square upon 8ml square. This is what we have derived in free electron theory. And also using the Bohr's theory, we can calculate the energy of the electron. But what in reality, we don't find isolated atoms. So whenever we are talking about any solid, any material that exists in nature, you cannot separate the atoms. All the atoms are embedded in a crystal. No? So where are the atoms present? The big question here is, when you don't find isolated atoms, you cannot find an atom separately or individually. So where are these atoms present? So everything for the band theory starts from here. So to understand, what we do is we see they are present in a crystal. So whenever you take a crystal, we say a crystal consists of n number of atoms. That n depends upon the atomic number of that particular crystal or particular element we are talking about. Now, if you see the arrangement, so how are these atoms arranged in a crystal? So we call this, they are arranged in a periodic fashion. Here I am talking about a silicon crystal lattice. When we say lattice, it is nothing but a periodic arrangement of atoms. Here we are seeing about 9 silicon atoms that are arranged periodically. Periodically means at regular intervals. Even in the last class, we have seen the distance between any two atoms is given by the lattice parameter A. So between any two atoms you take, they are separated by a distance A along a straight line. Now, this is what we call as a lattice. Now, if an electron is there in a particular atom, and there are many electrons like that because we have a number of atoms. Now, when we are talking about a crystal, we talk about a group of atoms which are arranged in a periodic fashion, and we cannot isolate one atom and talk. So, how are the electrons arranged in an atom? Now, if we are taking silicon, whose atomic number is 14. So, how do we write the electronic configuration of this? These are very basic things which we will try to understand so that we understand the band theory, how they are formed. Once you understand the energy levels, then it becomes very easy to understand the energy bands. Now, when we talk about the electronic configuration, for silicon, we write it as 1s2, 2s2, 2p6 and 3s2. This is what you all understand now. First orbit, there are 2 electrons. Second orbit, we are dividing it into s and p subshells. So s2 and p6 and then 3s2. So the total what we have here is 14. Now, when we are talking about these energy levels, so in 1s there are 2 electrons, and 2s there are 2, 2p there are 6, and 3s we have 2 electrons and then 3p, so we write 3p. So total it becomes 14. Now, if you see the 3-dimensional view, how they are arranged or how they revolve in different orbits. How do these electrons revolve in fixed orbits? So, if you see, this is the schematic view. We are talking, this is the nucleus. Nucleus we say is consisting of protons. 14 plus 14, that is why we are representing it. And this is the first shell, K shell, 2 electrons. And the second shell, it consists of 8 electrons, 2s2 and 2p6. Total 8 electrons. And then in the third one, there are 4. And if you see their movement, the pictorial view you can see here, they are moving in elliptical orbits. So different shells are shown here. This is the K shell, this is the L shell, and this is the M shell. If you are seeing in one dimension, we represent it in the form of a schematic view. But actually, this is the picture, how the electrons move in fixed orbits around the nucleus. Now, what we are going to understand here is, because of this periodic arrangement, the atoms are arranged in a periodic lattice. The outermost orbits of the neighboring atoms overlap with each other. So when we are talking about these atoms which are spaced in a periodic fashion, there is a chance or a scope that the neighboring atoms, means the adjacent atoms, their orbits may overlap with each other. The outermost orbits of the neighboring atoms may overlap with each other. So because of this overlap, what may happen? The electrons will have new interactions. Till now, if I'm talking about one atom, all the electrons in that particular atom are attached to the nucleus, and there will be a force of attraction between the nucleus and the electrons. That is how these electrons stay in closed orbits. That is what we understand. But now, because we are considering a large number of atoms, and these atoms, the outermost orbits of the atoms interacting with each other, what may happen? There may be changes in energies. The changes in energies are due to the interactions with the electrons of the neighboring atoms. So, if I'm talking about one atom here, nucleus, I may talk about now if there is another nucleus here, another atom, and I show the orbitals like this. Now, if they are coming very close, so there may be interaction between these electrons. So, the interactions with the electrons of the neighboring atoms, these electrons may interact with the electrons of the neighboring atoms. And also, there may be an interaction with the nucleus of the neighboring atoms. So, this one electron, maybe if it is far, in case of atoms with very large atomic number, where the orbits or the valence shell is very far from the nucleus, it may, if it comes very close to the atom of the next one, there may be an interaction of the electrons of the first atom with the nucleus of the second atom. That is what we are talking about. Interaction with the nucleus means electrons of first atom may be interacting with the nucleus of the second atom. So, there how the interactions vary, and therefore the energies may vary. Now, how we are going to see these interactions? We are talking about a lattice. So, this is how there is an overlap between the orbits of the neighboring atoms. So, here I have shown only 5 silicon atoms. So, they are arranged in a periodic fashion. You may have here and here there are many, but we are considering 5 to understand how they are interacting. So, this orbit of this atom and this orbit of this atom, if they are coming closer, these electrons may interact with each other. So, there may be variations in energies of the electrons that are interacting. Or sometimes these electrons, if it comes closer to this, it may come in interaction with the nucleus of this atom also. That is how we are discussing about why there will be a variation in energies of these electrons, even though they belong to the one particular orbit. Now we are representing, when we are talking about an electron, we have seen it is exhibiting wave nature, and we are using a wave function to represent the wave nature of electrons. So now we will talk in terms of wave function. Now I am considering 2 different atoms which are placed adjacent to each other, and if they overlap, if the 2 atoms or the orbits of the 2 atoms overlap with each other, then what may happen? So here this is atom A and this is atom B. Now the wave function of this atom is represented by psi A. This is wave function of this first atom, psi A. So this is how we are representing the wave function of the first atom, because the electron is in motion now. Okay, and we are considering it to exhibit wave nature. So we are representing it with a wave function. Now this is another atom B, whose wave function is denoted by psi B. So psi A and psi B are denoting these wave functions. Now, when these 2 wave functions overlap with each other, they come very close to each other, then what will happen? So there are 2 possibilities here. So when they are coming in phase, we talk about. So this is one atom, this wave, and this is the second atom, this is the wave. When these 2 are overlapping with each other, the resultant here is psi A plus psi B, and the wave is like this. And if they are coming out of phase, we say This is for psi A and this is for psi B. But the resultant here will be psi A minus psi B. So we are seeing here clearly that upon overlap, what is happening here? There is variation in the wave function. So that is how the wave function is getting modified. The modified wave function here is denoted by psi A plus psi B, and here it is denoted by psi A minus psi B. So once the wave function varies, the energy also varies. So upon overlap, what is happening? There is splitting of energy levels into two. So the same energy, we are talking about two different atoms which are in the same orbit. Same orbit in the sense, if this is in the first orbit or the second orbit, this is also in the same orbit, second orbit. So then what happens? There is splitting because of this overlap. Now what we are observing here is each atom has unique position. In a lattice, how these atoms are arranged, they have fixed positions in the lattice. And each electron has unique position. Why we are talking about unique is we have divided them into different orbits. Now 1s2, 2s2, 2p6 means first orbit, second orbit and third orbit. So the electrons have unique positions in their atoms and then unique interactions. So the interactions of the atoms and the electrons is unique, because if one electron is interacting with other electron of the second atom, it may be different for another atom. So therefore each electron will have different energy level, even though they belong to the same subshell of an isolated atom. So this is the main point we have to understand. When we talk about energy levels, so of one atom, okay, so this is E1, E2, E3 of the first atom. Now, if I take a second atom, similar atom, the energy levels should be exactly matching. That is what we understand. But because of these interactions, they will have different energy levels, even though they belong to the same subshell. As I told you, both of them may be belonging to the second subshell, but still they have a different energy level. And their energies after interaction are slightly greater or smaller. Like we have seen the wave function, it could be psi A plus psi B or psi A minus psi B. So they are slightly greater or slightly smaller than the energies in isolated state. If you say in isolated state, we talk about fixed levels. But when we see it as a crystal together, large number of atoms placed very close to each other in a periodic fashion, then because of the interactions, there may be variations in energies, and these energies after interactions are either slightly greater or smaller than in the isolated state. Now, if you are considering a solid of n number of atoms, just for an idea of how close they can be to understand these levels after variations, how close they will lie to each other. So, for a solid of n number of atoms, each of the energy level splits into n energy levels. So, forming a continuous band. So when I'm talking about n number of atoms, there may be n energy levels. So if I put all these levels together, it may form a bond. And in each band, what you have is a closely spaced energy levels. So I say this is the energy level of the first atom, then energy level of the second atom, third atom, fourth atom, and so on. I keep on placing these atoms. I'm not placing one on the other, because we have seen that there are slight variations in energies due to the interactions. So now when I have placed them close together, what is it looking like? It is looking like a band. It's a continuous band. Now when we are considering 1 mole of any substance, whenever we are talking about a substance, we talk in terms of mole. No? How many atoms are there in 1 mole? 1 mole consists of Avogadro number. This is what? This is Avogadro number of atoms. So 6.023 into 10 power 23 atoms. So 1 mole of any substance we take, it will have 6.023 into 10 to the power of 23 atoms. And now when I have to represent their energy levels, I may have to draw 6.023 or approximately 6 into 10 power 23 lines like this. So how many energy levels will be there? There will be 6 into 10 power 23 energy levels within a width of 1 electron volt. So if the width because I said the differences between them are very small, they are varying by very small energies. So within a width of 1 electron volt, I will accommodate 10 power 23 energy levels. So they look like a band. So these energy lines placed very close to each other appears as a band, which we call as energy band. Like you have seen here, I have drawn few lines here. This itself is looking like a band. But now if I am writing if I am representing 6.023 into 10 to the power of 23 levels in a width of 1 electron volt, so it will look like a continuous band, which we call as the energy band. Now, if you see the band formation, for a single atom, I am representing by E1. If I take two atoms, this is how they are interacting with each other. So, I may represent their levels by E1 and E2. Three atoms, E1, E2, E3. For the first atom, second atom and third atom. Now, I consider n atoms. Of course, I have shown here only 8 atoms. But even if you extend it to n number of atoms, where we are considering n as Avogadro number, and if the energy levels of all these atoms are placed like this. So these are the energy levels. They are placed very close to each other. Now, when there are more and more number of atoms being added, they are placed very close to each other. So for a single atom, when we are talking in terms of energy level. But when we are talking about a crystal together or a solid which consists of n number of atoms, we may consider them as closely spaced energy levels which form a band. Now, the width of the band depends upon the degree of overlap of the adjacent atoms, and it is the largest for the valence electrons. So, definitely the degree of overlap depends upon what? On the adjacent atoms, and it is very large for valence electrons. When you see, it will be the valence electrons who undergo overlap immediately. Okay, so the width of the energy bands near the nucleus goes on decreasing, whereas the inner electrons usually remain unaffected by the neighboring atoms. Because if you are talking about the inner electrons, they are very close to the nucleus, they are attached to the nucleus, and they remain unaffected. Those who are getting affected are the valence electrons, or the electrons which are there in the outermost orbit. They are undergoing this overlap with the neighboring atoms, and so their energies vary. Now, this is how we are seeing the splitting of energy levels due to interatomic interactions. What we have seen earlier, the same representation we are seeing here regarding the splitting of levels. So now here, because of the interaction, we are seeing that it is split for 3, 4. We can continue it or extend it for n number of atoms. Now, whatever we have seen till now, I have just put it in a single slide. So, if I am talking about individual atom, you have the nucleus at the center and electrons revolving around in fixed orbits. And their energy levels are represented. They are represented by sharp or discrete. They are discrete energy levels. So, I can represent the energy levels of the first orbit, then 2s, 2p and so on. These are the energy levels. Now, the same atom, I look at it in a crystal. A crystalline solid which consists of 10 power 23 atoms which are very close together. So here we are showing only 24 atoms, but there are more actually. So now because of the interactions, what is happening? There is overlap here. There are a number of levels which are overlapping and they are forming band. This is for 1s. So this is for 2s. All overlapping. Electrons of different atoms in the solid. Because of the interactions, the energy levels varying and the energy levels are spaced very close and they are forming bands like this. So you have different levels here. Okay, so this is how we are now shifting from energy level to energy band. Now if you consider the sodium metal. So when isolated sodium atoms are brought together to form a solid, then the energy levels of the valence electrons spread into bands. I told you that is the valence electrons that are participating or that are interacting with the neighboring atoms, valence electrons, and because of that, how the lines are being spread. The energy levels are getting converted into bands. So this is 3s if you show for an individual atom. But when you see in a crystalline solid, there will be n number of atoms. So all the valence electrons, if you have to show in this particular level, so you will represent it by a band. So what we are basically talking about is how is the band theory originating or how are the bands formed? That is what we are understanding. Now the energy bands in solids are very important in determining many physical properties of the solids. So not only this, we are also talking about their electrical properties, thermal properties also. And what are the bands that are possible here is the valence band and the conduction band. We are talking in terms of two, valence band and conduction band. So what is this valence band? The band corresponding to the valence electrons. If I represent the energy levels of all the valence electrons put together, all valence electrons, whatever their energies are, they are very closely spaced even after interaction. So they are form a band and we call it as valence band. So what is valence band? It is the band corresponding to the energies of the valence electrons. Then we have a conduction band. What is conduction band? The band corresponding to the conduction electrons. What are conduction electrons? Conduction electrons are free electrons. When we say conduction electrons means which help in conduction. Which electrons will help in conduction? Only free electrons help in conduction. So now those electrons which can be made free from the outermost shell, we call them as free electrons. And if I represent the energies of all these free electrons, they form a band and we call it as conduction band. So the valence band is representing the energies of the valence electrons and the conduction band represents the energies of conduction electrons or free electrons. Now, if I represent, this is the valence band which represents the energies of all the valence electrons. Now I place the energy levels of all the conduction electrons also. So we get a band. So this is a conduction band. Now in between the valence band and the conduction band, there may be a gap. There may be a gap. We are going to discuss about this gap. So the gap between them is called forbidden band or forbidden energy gap. This is called forbidden energy gap. So the gap which is there between the valence band, or I say specifically between the topmost level of the valence band and the bottom level of the conduction band. So this gap we are calling it as forbidden gap or the forbidden band. Now in a solid, many atoms are brought together. No, we have seen, and the split in the energy levels form a set of energy bands and they are very closely spaced. Now what we have seen, when we are separating them as valence electrons and conduction electrons, we have a valence band and a conduction band separated by a forbidden band. And then coming to the overlapping of these atoms, the overlapping is more if the equilibrium spacing is less. If the spacing between the atoms, the equilibrium spacing, it depends upon the overlapping of the atoms depends upon the equilibrium spacing. So we are going to see or understand it with the help of this diagram. Now if I am plotting a graph for R, that is R, here we are talking about equilibrium spacing R naught for different elements. No? So along the x-axis we are taking the spacing, equilibrium spacing, and along the y-axis we are taking the energy. Now when the equilibrium spacing is very less, in case of metals where the equilibrium spacing is very less, these bands are overlapping with each other. I say this is a valence band and this is a conduction band. And then in case of semiconductors which are partially conducting, there may be a small gap between the valence band and the conduction band. But if you see in insulators, this gap between the valence band and conduction band is very big. Now we are going to classify the materials based on this concept. So what is the concept? With the equilibrium spacing, this overlap is varying. It is different for metals, semiconductors and insulators. So we are classifying the materials also based on the energy gap. So how is the energy gap obtained? When we are seeing the equilibrium spacing versus energy, if there is an overlap or if the distance between or a gap between the valence band and the conduction band is very small or very big, based on that we are going to classify. Now on the basis of forbidden band, the energy gap of the solids are classified into insulators, semiconductors and conductors. So first we will see what are conductors here. As we have seen, this is the valence band. Valence band here represents the energies of all the valence electrons, and this is the conduction band representing the energies of all the free electrons or conduction electrons, and there is no gap. In fact, these two bands overlap with each other. There is an overlap between the two. Means, what does this symbolize? This represents that these electrons from the valence band can go to the conduction band very easily. They can be made free easily. So if they are free, they start conducting. So that is why we are calling them as conductors. So with the help of energy gap, how you are understanding or how you are classifying is, if there is no gap or if there is an overlap between the two, then you call them as conductors. Then we have semiconductors. In semiconductors, there is a gap between the valence band and the conduction band, but it is small, of the order of 1 electron volt. The valence band and conduction band are separated by a small forbidden band of the order of 1 electron volt. Then we have the insulators. In insulators, if you see, the forbidden gap is huge. So of the order of 7 to 8 electron volt, depending upon the depending upon the insulator we are talking about. So this is the valence band and this is the conduction band, and the gap between them is big. So how we are classifying it? Based on energy gap. Energy gap is not there or there is an overlap, we call them as conductors. If the energy gap is very small, of the order of 1 electron volt, we call it as semiconductor. And in insulators, it is very big. The forbidden gap is very big. Now we'll try to understand about this conductors. In conductors, there is no forbidden gap. Means the valence and the conduction band overlap with each other. So this is the valence band, this is the conduction band. This green one is the valence band and this yellow one, this is the conduction band. So there is an overlap between the two bands. So what is happening? The electrons from the valence band freely enter into the conduction band. So these electrons have come from the valence band to the conduction band. So they are coming freely. So once they are in the conduction band means they are free and they can conduct. So even at room temperature, a large number of electrons are available for conduction. So that is what we see here in a conductor. Why it is a good conductor means even at room temperature, they have a large number of electrons in the conduction band which are ready to conduct, which are free. So we call them as good conductors. And without any additional energy, metal contain a large number of electrons. Therefore, we are calling them as good conductors. Without additional energy means we are keeping it at room temperature. We are not increasing the energy, neither thermal nor electrical energy we are supplying. So without any additional energy, these valence electrons are going to the conduction band. Okay, so that is why we call them as good conductors. Now, when a substance is placed in an electric field, now suppose if this conductor is placed in an electric field, the electrons will gain potential energy. And then what happens? The conduction band and the valence band may overlap and there is additional energy for the electrons and cause the current. So the movement of electrons gives rise to current. And what is the reason? Because there are allowable energy levels directly above the initial state. Suppose I have electrons here, directly above it there are allowed energy levels. There is no gap between them. That is why they are overlapping and they have enough free electrons. That means electrons in the conduction band. And these conductors have very low electrical resistance. See, when we have studied the electrical theory, free electron theory, we understood that those two theories could not explain the temperature resistance or the effect of temperature on resistance. But here what we are trying to understand is how the temperature, with the temperature, the resistance varies. So the conductors are having very low electrical resistance. Low electrical resistance means if the resistance is less, so the conductivity will be high, they will conduct more. So that is what we are trying to understand. With low electrical resistance, they become good conductors. So the opposition to the current flow is less. So they allow the current to flow very easily. So what are these applications where we are going to use these conductors? Metals like iron and copper that can conduct electricity are made into wires and cables for carrying the electric current. So initially we used to have only copper cables for carrying the current because copper is a good conductor. Now we have many types of materials which are used for carrying current, but initially the conventional thing is the copper cables. Now other examples for good conductors are gold, copper, silver, aluminium. All these are very good conductors. Now coming to insulators. So in case of insulators, the forbidden band is very wide. So if you see in the diagram here, this is the valence band, this is the conduction band. Now the band gap between the valence band and the conduction band is very wide. Okay, due to this, what is happening? Electrons cannot jump from valence band to conduction band. So these electrons cannot move to the conduction band easily because there is a gap. If they have to go from valence to conduction band, they will have to overcome this band gap. Only then they can be made free and go into the conduction band. So when we talk about insulators, they have completely filled valence band and completely empty conduction band. All the valence electrons are represented in the valence band, and because these electrons cannot move here, the conduction band is completely empty. So these blue dots are representing the electrons. So if you see, the valence band is completely full, but if you see the conduction band, it is empty. Means the valence electrons cannot be made free very easily because of this band gap. So the resistivity of insulators is very high. Because of this band gap, we are saying that the resistance is very high. and insulators are bad conductors of electricity. That is why we call insulators or bad conductors. They do not conduct, so we are calling them as bad conductors of electricity. So an insulator is a material that has high electrical resistance and it does not allow the flow of current. So when you are asked to define what an insulator is, it is a material which has high electrical resistance, means which resists the flow of current. So we are calling it as insulator. Now there are no free electrons. What we have seen in the figure now, there are no free electrons, so they do not conduct electricity. They may conduct electricity only at very high temperatures or when subjected to high voltage. So maybe we are supplying thermal energy or electrical energy. Only then you may be able to shift the valence electrons to the conduction band. And if such a thing happens, what we call such conduction, there is a breakdown. The breakdown of the insulator happens and only then there is conduction. That is what we understand about insulators. And where we are going to use these insulators, they are used for protection basically. So protection against shock or protection against high voltages and also prevention of electrical short circuits. So because there are no electrons in the conduction band, so it cannot conduct continuously. So thereby it prevents the electrical short circuits between cables. So the materials, examples of insulators are rubber, glass, wood, air. Air is also a very good insulator. Mica, plastic, paper, all these are examples of insulators. Now coming to semiconductors. In semiconductors, the forbidden gap is very small. So forbidden gap is very small. We have mentioned here 0.7 electron volt for germanium and 1.1 electron volt for silicon. That is why I said it is of the order of 1 electron volt. I said ranging from 0.7 to 1.1. Germanium and silicon are very two good semiconductors. So now if you are seeing here, this is the valence band, this is the conduction band, and there is a small gap. There is a small gap between the two, and this gap depends upon the material. Usually for insulators we say of the order of 1 electron volt. If you speak specifically for germanium it is 0.7 electron volt and for silicon it is 1.1 electron volt. Now at 0 Kelvin there are no electrons in the conduction band and the valence band is completely filled. If I have taken an insulator and if it is at 0 Kelvin, this valence band is completely filled. You have electrons filled here, but this conduction band is unfilled. There are no electrons here at 0 Kelvin. But as the temperature increases, electrons from the valence band jump to the conduction band. So when you supply temperature, means when the temperature increases more than 0 Kelvin, even at room temperature, some of the electrons from the valence band, they move to the conduction band. So the conduction band is partially filled. So the valence band electrons moving to the conduction band means they are free, means they start conducting. So at 0 Kelvin, there are no free electrons, means no conduction. They will behave like insulators. At 0 Kelvin, you see the conduction band is completely empty, means there are no free electrons. No free electrons means no conduction. So they behave like insulators. So we say that semiconductors at 0 Kelvin, they behave like insulators. But on supplying energy, here we are increasing the temperature. Then some of the electrons move to the conduction band. They become free, they start conducting. And their resistivity varies between 10 power minus 14 to 10 power 7. This is the resistivity in semiconductors. I told how resistivity affects the conductivity. If the resistance is more, the conductivity flow is very less. It will not allow the electrons to move. Then there will be no current. Now, in case of semiconductors, the greatest advantage is they block or allow the current flow. and have total control over it. When you want to block it, you can block. When you want to allow the current to flow, you can allow the current to flow. That is why semiconductors have got lot of importance in electronic circuits. Wherever we are using semiconductors because of this reason. They have total control over the flow of current, and they also can be modified by adding impurities. Okay, the addition of impurity to a semiconductor, we call it as doping. The process of adding an impurity to a semiconductor is called doping. And when you do doping, their properties get modified. And the electrical conduction inside the semiconductors is due to the movement of electrons and holes. So this is also one important thing we need to understand. In case of conductors or in free electron theory, what we have considered is the conduction or the current is due to the flow of electrons. But here, the movement of electrons and holes contribute to electric conduction. And the examples for semiconductors are silicon and germanium we have seen. Now coming to the applications. There are a lot of applications for semiconductors. So we use them in television, in advanced medical care, personal computers, mobile phones and smartphones, automobiles. In every area of our life, now we see the applications of semiconductors. So now what we are going to do in the rest of our module is study about semiconductors, how the charge carriers are in a semiconductor, how do they conduct. All these things we are now going to focus mainly on semiconductors. Thank you. See you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.